Hi, welcome to Lecture 13, Electronic Configurations and Drawing Lewis Structures. This is our first Gen Chem lecture, and I hope you enjoy. Any electron in an atom can be described by four quantum numbers. N, the principal quantum number, which represents the shell number. L, the azimuthal quantum number, which represents angular momentum. ML, the magnetic quantum number, which represents the orientation of the orbital, and ms, the spin quantum number. The Pauli exclusion principle says no two electrons of a given atom can have the same four quantum numbers. The position and energy of an electron, described by its quantum number, is known as its energy state. Here we look at the principal quantum number n. It's known as the electron shell. It describes the energy level on which the orbital resides. It corresponds to the values of the Bohr model. The values of n are integers greater than or equal to 1. As n increases, the electron is less tightly bound to the nucleus. So here we have the nucleus with four shells. N equals 1, n equals 2, n equals 3, and n equals 4. The next quantum number is angular momentum quantum number, or L. This describes the shape of the orbital. It's known as the subshell. The values of L are integers ranging from 0 to n minus 1, or the shell minus 1. Using letter designations to communicate the different values of L, the shapes and the types of orbitals are listed below. When you have the L value of 0, you have an s orbital. When the L is 1, you have a p orbital, 2, d orbital, and so forth. The magnetic quantum number describes the three-dimensional orientation of the orbital. The allowed values of ml are integers ranging from negative L to positive L. This determines the number of electron orbitals in each subshell. On any given energy level, there can be up to 1 s orbital, 3 p orbitals, 5 d orbitals, 7 f orbitals, 9 g orbitals, 11 h orbitals, and 13 I orbitals. If we look at the periodic table, we can see that the orbitals are broken down into groups. We have the s orbitals on the first two columns, the d orbitals in the transition metals, the p orbitals to the right, and the f orbitals for the lanthanides. The representations of orbitals can be shown in an energy diagram. As n increases, the spacing between energy levels becomes smaller. In the Aufbau diagram, electrons fill low energy orbitals first. Orbitals with the same energy are said to be degenerate. So the 2p has 3 degenerate orbitals. The 3d has 5 degenerate orbitals. N1 is the lowest energy. As we increase out to N2, the energy is increased, and N3 it is even further increased. So if we look at the lithium, lithium has 3 electrons. We look at the ground state, we fill the orbital with 2 electrons. Each orbital can hold a maximum of 2, and then we jump up to n equals 2, and we fill that last orbital, or N2 shell, with 1 electron. The total electron count is 3. Orbitals are filled in order of increasing energy with no more than 2 electrons per orbital. The electron configuration of lithium is 1s2, 2s1. So, here we have a list of several elements. You can look at the total electrons, 3, 4, 5, and so on, and the orbital diagrams. Notice that as we go down the chart, we just add 1 electron to the orbitals. When we get to carbon, however, you'll notice that when we add the electrons, they're spin up, spin up. The reason for this is you want to fill the degenerate orbitals before you go back and start pairing them. So when you get to oxygen, you have 8 total electrons, and then we start to pair them up again. And in fluorine, we have 2 pairs in the 2p orbitals, and neon, we have 3 paired in the 2p orbitals. The total electron count in the 2 shell, 2s and 2p, is 8 electrons. The maximum amount of electrons in the noble gas to get stability is 8 electrons. So we can write this as Ne, or Ne bracket. So if we look at sodium, it has 11 electrons. So we could fill up 2 electrons in the 1s orbital, 2 electrons in the 2s orbital, 6 electrons in the 2p orbital, and 1 electron in the 3s orbital. So the electron configuration of this is 1s2, 2s2, 2p6, 3s1, or neon 3s1. The neon bracket basically represents the full shell noble gas prior to the sodium. Hund's rule for degenerate orbitals, the lowest energy is attained when the number of electrons with the same spin is maximized. So how does electron configuration, how do we know the order? Well, this chart shows that if you follow the arrows, you can get the order of 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6, and so on. So if we look at helium, the atomic number on the periodic table is 2. That means there are 2 electrons. So if we fill up the orbitals, we get 1s2, or helium. If we look at neon, the atomic number is 10. It has 10 electrons. So if we fill up the orbitals, it goes 1s2, 2s2, 2p6, or neon bracket. If you count up the superscript numbers, it will equal 10. 2 plus 2 plus 6 equals 10. If you look at Krypton, the atomic number is 36. Electron total is 36. So it is 1s2, 2s2, 2p6, 3s2, 3p6, 3d10, 4s2, 4p6. If you add up the superscript numbers, you end up with 36, or 2 plus 2 plus 6 plus 2 plus 6 plus 10 plus 2 plus 6. It's much easier just to write out Krypton bracket. So if we look at boron, helium bracket 2s2, 2p1, calcium, argon bracket 4s2, and calcium plus 2 ion is argon bracket. The reason for this is the calcium 2 ion, we remove 2 electrons. So you'll notice the 4s2 orbital is empty. So it just drops down to the 3p6, or argon bracket. So electrons in the outer shell are valence electrons. They are the ones to bond. Now that we understand electron configuration, we can start to draw Lewis structures. The Lewis symbol for an element consists of the chemical symbol for the element plus a dot for each valence electron. Carbon, atomic number 6, has 6 electrons. We know the electron configuration of carbon is 1s2, 2s2, 2p2, or helium bracket 2s2, 2p2. Therefore, there are 4 outer shell valence electrons. s2 plus p2, 2 plus 2 is 4. So we can draw it, carbon, with 4 electrons surrounding it. We fill the electrons clockwise, 1, 2, 3, 4. If we look at sulfur, atomic number 16, it has 16 electrons. The electron configuration of sulfur is neon bracket 3s2, 3p4. There are 6 outer shell valence electrons. Again, we fill it clockwise, 1, 2, 3, 4, and then we have 2 more electrons to make the 6. So we start pairing them up. 5, 6. If we look at atomic number 8, oxygen, it has 8 electrons. The electron configuration of oxygen is 2s2, 2p4. So there are 6 outer shell valence electrons. Same as sulfur, it's just up a period on the periodic table. So the Lewis symbols for sodium are shown here: magnesium, aluminum, silicon, phosphorus, sulfur, chlorine, and argon. Notice that as we go down the chart, the electron configuration increases by 1 electron in each row. And with the Lewis symbol, we basically just add 1 electron as we go around until we come to argon, which has 8 electrons, which is a full octet, which makes it a stable atom. Atoms gain, lose, or share electrons to achieve the same number of electrons as the noble class closest to them on the periodic table. The Octet Rule. Atoms tend to gain, lose, or share electrons until they are surrounded by 8 valence electrons. They want that stability of the noble gases. Carbon has 4 valence electrons. Each oxygen has 6 valence electrons shown in red. The total valence electrons is 16. 2 electrons between atoms can be drawn as a bond or a line. Less electronegative atoms are placed in the center, excluding hydrogen. So here we have carbon. It has 8 electrons around it. Those 8 electrons, 4 of them are from oxygen, 4 of them are from carbon. We can take 2 electrons and pair them up and draw a line. So we have 4 lines. On each oxygen, to the left and the right, there are 4 remaining electrons drawn in black. So if we look at methane, the methane carbon has 4 valence electrons. The methane hydrogen has 1 valence electron. So the total valence electrons is 4 plus 4, which is 8. So we can draw it 2 ways. The first way is we can just draw the dots. We surround the carbon with 8 dots. Hydrogen, being a 1s2 orbital, can only have 2 electrons. The carbon can have up to 8 electrons. So we fill up that and we can compare them and then draw the lines to form methane. If we look at ammonia, ammonium nitrogen has 5 electrons. The ammonium nitrogen has 1 valence electron. So the total number of valence electrons is 8. We have 2 for each line, 2, 4, 6, and then 7 and 8 are the lone pair on the top of the nitrogen. A little bit harder example is looking at the nitrate ion. The nitrate nitrogen has 5 valence electrons. Nitrate oxygen has 6 valence electrons. There's a -1 charge on the ion, so we add 1 valence electron. So the total of valence electrons is 24. We put the least negative electroatom in the center, which is nitrogen, and then we just surround it with 8 electrons to get the structure. The question then is, where's the negative charge? This brings us to formal charge and resonance. So the question is, which atom has the negative charge? When we look at the nitrate ion, NO3-, we need to figure this out. So we use the formula for formal charge as valence electrons minus non-bonding electrons plus bonding electrons divided by 2, also known as the number of bonds. So if we look at nitrogen formal charge to the right, nitrogen has a valence shell electron count of 5 minus the non-bonding electrons of 0 plus the number of bonds, which is 4, which equals +1, 5 minus 4. If we look at the left oxygen, the valence number of electrons is 6 minus the number of non-bonding electrons, which is 4, plus the number of bonds is 2. 6 minus 6 is 0. So there is no formal charge on the left oxygen. If we look at the bottom and right oxygen, the valence shell electron count is 6. If we look at the non-bonding electrons, there are 6. Those are the dots. And if we look at the number of bonds, there's 1. 6 plus 1 is 7. 6 minus 7 is -1. So the formal charge on the bottom and right oxygens is -1 per atom. So there are 3 different ways we can draw the nitrate ion. These are shown in the bottom. The negative charge can rotate between oxygen atoms. To draw from one structure to the other, we use a double-sided arrow, and these are called resonance forms. The total resonance structure is on the bottom right, where each oxygen atom carries a -2/3 charge, and the dotted arrows show that the electrons are rotating between oxygen and nitrogen bonds. So the Lewis structure of sulfuric acid. First, we find the total number of valence electrons. Sulfur's electronic configuration is neon bracket 3s2, 3p4, 3d0. So it has 6 valence electrons. Oxygen is helium bracket 2s2, 2p4, which is 6 valence electrons. Since there are 4 oxygens in sulfuric acid's molecular formula, we times this by 4 to get 24 valence electrons. Hydrogen is 1s1. There's 1 valence electron times 2 hydrogens equals 2 valence electrons. The total number of valence electrons in sulfuric acid is 32. We then place the least electronegative atom in the center, excluding hydrogen, and draw the core bonds. Once we have done that, we start placing the lone pairs on the atoms to satisfy the octet rule. Notice that the oxygen and sulfur each have 8 electrons around them. Hydrogen has 2. We then calculate the formal charge. For sulfur, it's 6 minus 4 plus 2. For the bottom and top oxygens, it's 6 minus 7, or negative 1. And the left and right oxygens are neutral, which are 6 minus 6, which equals 0. The last step is we want to minimize the charge separation. Atoms with a bunch of charge separated all over are quite unstable. So to do this, we can push 2 of the electrons down from the oxygen into the sulfur. That will cause the sulfur to have a +1 charge, and that oxygen on the top to have no charge. We can then do the same to the bottom oxygen and push 2 electrons up, neutralizing the sulfur. There are no charges on the atom then, and this is the most stable structure. But you will notice that the sulfur now has more than 8 electrons, violating the octet rule. The reason for this is sulfur can have more than 8 electrons by accessing one or more of its d orbitals. Recall the electron configuration of sulfur's neon bracket 3s2, 3p4, 3d0. Basically, the electrons can jump into those d orbitals. So if we look at the phosphate ion, PO43-, we calculate the number of total valence electrons, and we come up with 29. We place the least electronegative atom in the center, which is phosphorus. We surround each atom with 8 electrons to form the intermediate shown on the bottom. We then calculate the formal charges, and we find each oxygen has a -1 and the phosphorus has a +1. To neutralize the charge separation, we draw one arrow from one of the oxygens into the phosphorus, and that yields us the Lewis dot structure. Again, phosphorus can have more than 8 electrons through accessing its d orbitals. And there are exceptions to the octet rule. Incomplete valence shells, such as a 7-electron species, as free radicals with unpaired electrons, like the methyl radical. 6-electron species, like carbines. There are also other rules, like the duet rule of the first shell of helium, or the 18-electron rule of transition metals. These will be talked about in a future lecture. Thank you.